Hey guys, and welcome to our chemical reactions unit, I guess, is the opening to our new unit. We're going to start with a review of stuff we should know from grade 10. So it's not actually the review like end of unit review. This is a let's get started kind of review. So start at the very beginning. All reactions between different elements or different compounds, maybe would be a better word, can be written as either words or as a chemical equation. So for example, I could write as words, hydrochloric acid and magnesium metal will yield hydrogen gas and magnesium chloride. Now that's a mouthful and it's kind of ugly to look at, if I'm being quite honest. And so we usually use chemical equations instead. Hydrochloric acid, HCl, which is usually diluted in water, plus magnesium metal, magnesium, which will be a solid metal, will react to form or will yield hydrogen gas, and hydrogen is one of our diatomic molecules, so it always comes paired. And it'll give me magnesium chloride. Magnesium and chlorine. Magnesium's got a +2 charge. Chlorine's got a -1 charge, so that would balance it. There we go. Oh, and magnesium chloride. I believe that's soluble, so I'm going to say aqueous. I'd have to double check. So that would be the equation written as a form. The word equation written in like symbolic equation form. Quick reminder of the diatomic elements. My good friend Hofbrinkel the clown. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. It's basically, all of your halogens, hydrogen gas, and the other two are oxygen, nitrogen. So, little note. Something that I did this year that we hadn't done previously. All of these. Aqueous, gas, solid, liquid. We're in grade 11 now, right? The states of our substances are becoming more important. So, for example, we just finished our gas unit. If you want to know if you can use some of those gas laws to figure stuff out about this equation, you need to know if it's a solid, a liquid, or a gas. And so, to show what state a chemical is in, we use G for gas, L for liquid, S for solid, and AQ, aqueous, means dissolved in water. You'll find a lot of the time your chemistry is aqueous. Almost always the stuff you work with are aqueous or liquids. Sometimes you form a solid or you form a gas, but normally to make stuff react, a lot of the time you'll see it in liquid or aqueous form. And you just write that in brackets next to your reactants or your products. So you can see like there's aqueous, gas, magnesium metal was a solid, hydrochloric acid was probably aqueous. I say probably because if it was a liquid, that means it's pure, and that would be absolutely terrifying. Usually we dilute acids. Moving on, balancing equations is something we should be familiar with, and I know you guys are because we started the year with a little bit of extra practice. But quick rehash, there has to be equal numbers of the same atoms on each side of an equation. So you start with a substance that has the lowest subscript. Whoops, that should say highest subscript. That tends to make it easiest. Start with the highest subscript and fill in your coefficients. So I look at this equation here. I see I've got a Cl2, so I need 2 chlorines over here. 2 chlorines on this side gives me 2 chlorines on this side. This also means if I have 2 chlorines, I also have 2 H's. So, okay. Get my eraser going here. And I froze it. Anyways, if I got 2 H's on this side, I need 2 on this side. Hey, look, I've already got 2 on this side. And if I got 1 magnesium, I need 1 magnesium. And then I should be all balanced. Double check. 2 H's, 2 H's. 2 Cl's, 1 set of 2 Cl's. 1 times 2 is still 2. 1 magnesium, 1 magnesium. I've checked everything. I should be good to go. So it's 2, 1, 1, 1 for this particular reaction. We'd say this is 2, 1, 1, 1. Those are my coefficients, and it works nicely. For our next one, where's my biggest? Maybe this 3 here. I have 3 SO4s. So remember, if you have polyatomics, they can travel together. Polyatomics travel together. Now, they don't always, but when they do, balance them. When polyatomics travel together, balance them together. Otherwise, I have to look at oxygens and sulfurs and all that separately, and oh, what a pain. But I got 3 sulfates there, which means I need 3 sulfates on this side. Now, if I have 3 sulfates, I also just gave myself 6 potassiums. Ooh, so I'll need a 6 there. So that gives me 6 potassiums. It also gives me 6 bromines. So where's bromine? Oh, it's over here. So how do I make 6? 2 sets of 3. That gives me 2 aluminums. And hey, look, I've already got 2 aluminums. Nice. So that should be balanced, and life is good. Again, you guys had tons of practice earlier in the year, so I'm thinking balancing probably won't be too bad, but we'll brush up on a little bit at the beginning of this unit too. More stuff from last year. The types of reactions. So there are 5 basic kinds of chemical reactions, and we find that almost every reaction follows one of these 5 types. So the first is a decomposition. It's when a compound is broken down into 2 other substances. So you go from one thing, a compound, into 2 things. So for example, nitrogen dioxide will decompose, there's a key word, oh, it's decomposition, to yield nitrogen gas and oxygen gas. So if you were to actually look at it, you've got nitrogen dioxide. I know it is decomposing, so it's just going to break down right away. It's going to form nitrogen gas and oxygen gas. Nitrogen is diatomic. Oxygen is diatomic. Those are both Hofbrinkel ones. So they always have to come paired. You never find them on their own. And then I could balance it. 2 N's and 2 N's, that's good. 2 O's on this side means I would need 2 O's here. Oh, I just increased my N's to 4, so I need 4 N's as well. The next common kind of reaction is a synthesis, when 2 things combine to form 1 thing. So decomposition is 1 splits into 2. Synthesis is 2 combines into 1. They're kind of opposites of each other. So for example, iron 3 metal and iron oxygen gas will combine to produce rust, which is iron 3 oxide. So I've got iron metal plus oxygen gas, which is O2, combines to form iron oxide. In this case, iron 3 oxide. Single displacement is your next common type of reaction. So we're going to pay attention. This is 2 up here, breaking down into 1. In a single displacement, a compound breaks apart, and one part of the compound switches with a different substance. So hydrochloric acid reacts with magnesium metal to release hydrogen gas. What you see in this reaction is that the hydrogen, because it's positive. Okay, here's how you figure these ones out. You look at the one that's not attached, magnesium. Does it form positive or negative ions? Well, magnesium, it's in row 2. It's usually got a +2 charge. So magnesium wants to be positive. So you look at the second part, HCl. Which of those is positive, hydrogen or chlorine? Well, chlorine's definitely a -1, right? It's way down in group 7. So our hydrogen's probably also our positive one. So what happens in a single displacement is that the ones that have the same sign swap. So hydrogen and magnesium are going to swap. So hydrogen ends up left on its own, and magnesium ends up in the compound. So you go from hydrochloric acid plus magnesium metal to hydrogen bumped out, so it becomes hydrogen gas, and magnesium goes in, turns into magnesium chloride. So you just get the ones, it's often the positive ones. It's often a metal getting bumped out because acid plus metals are really common reaction. But you do occasionally have it where the negative one is bumped out. If you were to have a negative, a compound that normally forms negative ions on this. If I had chlorine, it could bump out, or fluorine, it could bump out chlorine or something like that. Double displacement, same idea, but now it's 2 compounds forming 2 new compounds. So again, the big thing is a swap. So this, you got 2 compounds, so they're both going to have a positive side and a negative side. And so the easiest way is to pick one and swap them. I prefer to do the positive side. So if I was going to do this swap, I say, okay, this is what I've got. I'm going to change my potassium and my hydrogen. That's all I got to do. So I'm going to have HOH, which is water, H2O, and I'm going to have KSO4. And then once you've done the swap, you have to check your charges. So sulfate is a -2, which means I would need 2 Ks. Oxygen's a -2, which means I'd need 2 H's in that compound. And once you've written it out, then you can balance it. So basically, you're just swap. The way I do it is swap the positive ones. You could swap the negative ones as well and get the same answer. Just don't swap them both. If you swap both positives and both negatives, you're back where you started from. And that doesn't do any good. And the last one, probably the hardest one to balance, but one of the easier ones to actually usually write, is combustion. So a hydrocarbon. And a hydrocarbon is anything that just has hydrogen and carbon in it. Hydrocarbon. Hydrogen and carbon. Pretty straightforward. It's got hydrogen carbon in it. You react it with pure oxygen gas, which is, again, a diatomic. It always comes in pairs. And you will produce carbon dioxide and water vapor. There's no wondering what the products will be. The products are always CO2, H2O. Another word for combustion is burning. You take something, combine it with oxygen, it gives you carbon dioxide and water. So, for example, we have methane, CH4, and you're like, hey, look at that. It's made of carbon and hydrogen. It's a hydrocarbon. And if, say, methane is burned or combusted, right away you know, oh, okay. So then whatever they're giving me, it's plus oxygen, gives me CO2, gives me H2O. It's always going to be that. O2 gives me CO2 plus H2O. So if you got combustion, you got burning, that'll do. That's the reaction you'll be looking at. Finally, something you should be able to do, now that you've refreshed those kinds of reactions, is predict the products of a reaction. So if I give you the type of reaction you've got and what the reactants are, you should be able to tell me what you're going to end up with. So for example, electricity is applied to water, causes it to decompose. I'm starting with water, which is a liquid. And I'm decomposing. So what does decomposition mean? Take one thing, break it into two. Well, what can I break water into? I only see two options here. I could get hydrogen, and I could get oxygen. The only thing you got to remember is that hydrogen's diatomic, oxygen's diatomic, and they're both gases. And then your final step would just be to balance it. I got two O's here, so I need two O's there. That gives me four H's, so I need four H's. There we go. I have a beautiful, balanced decomposition of water. Another example, I've got zinc, which is probably just a chunk of zinc, so that'll be a solid, plus copper sulfate. Sulfate has a -2 charge. Copper's usually a +1, so I'm going to need 2. That should probably say copper 1 sulfate, actually, if it was going to be written better. They're going to give me a single displacement reaction. Single displacement means the positive ones switch spot. I know zinc is a metal, which means it's almost always going to be positive, so I'm going to end up with zinc sulfate plus copper metal. And if these are reacting, copper sulfate I know is soluble. We'll talk about solutions and how to know things are soluble later. Sulfates usually are, but we'll talk about that in another unit. Maybe actually be grade 12 we talk about solubility. Yeah, we'll see. And so now the question is this formula correct? Well, I can't actually know for sure because I don't know what the charge on zinc is supposed to be because it didn't tell me here if it was a zinc 1 or a zinc 2. Let's call it a zinc 2. That'll just make balancing a little easier. So if I want to balance it, it'd be a zinc 1. That way it takes sulfate's -2 charge goes down there. Anyways, let's balance it. 2 zincs, 2 coppers, 2 coppers. I should be balanced. But the important part is ignoring the balancing and the states. The important part for this is, would you know that if I gave you zinc and copper sulfate, that you would get zinc sulfate and copper? Regardless of what the actual chemical things look like, you should know that based on the types of reactions, and you should be able to predict that. So we're going to do a bit of practice with that in a little while, but that basically sums up our review of the grade 10 chemistry stuff that you should know. So hopefully that was all somewhat familiar to you, and I will catch you guys next time.